Okay, so hi, thank you all for coming. So as was just mentioned, we're going to talk about category theory and how it can be used to think about functional programming. Before we begin, though, I'd like to have a little small introduction to get us sort of in the right frame of mind for this talk. So if you happen to be following the Haskell community, you probably have heard of someone called Edward Kmet. I'll use him as an example of someone who's very proficient in category theory and the sort of person that inspired this talk. So this is a somewhat edited quote from Reddit. Someone is telling us how they discovered some cool new idea that can be used in functional programming. And Edward Kmet says that this is just the right-con extension encoding of something. Another well-known idea. And so when I see something like this, although I have no idea what the con extension is, the first thing that comes to my mind is there a left con extension? Using that will give us another useful, cool new idea in functional programming? But delving a little bit deeper, there's something very profound going on here. So what we see here is an example of using category theory as a tool to derive one idea from another idea. So this is an example of how category theory can be used to explore what I'll call the idea space. So what do I mean by the idea space? So there are many useful ideas in the world and in the world of functional programming. And every once in a while, someone comes up with a great new idea. And if we're lucky, maybe there are some other follow-up ideas, maybe not as great, not as significant, but still nice to have. And so have this little cluster of new ideas. And somewhere else, someone might discover another idea with its own follow-up ideas. And rinse and repeat, and we have what I'll call now the idea space, various different ideas. The problem with this picture that I'm showing is that how do we connect these ideas? So every idea here requires some kind of stroke of genius. You have to kind of discover them on your own and have that idea. But once you discover that, it doesn't really help you finding other great ideas. So for example, how will you connect this round shape idea with the square shape idea? They're obviously quite different, so you can't really see the similarity and you won't be able to actually connect them. So what we're missing is some tools to explore the idea space. And in this talk, I'll try to show how category theory can be used, can provide us with various tools to help us explore this idea space and connect the various different shapes we have here. So now we might be able to actually see a connection between a circle and a triangle. And sometimes they might even help us find brand new ideas. So category theory will help us explore the idea space in a way that's much more mechanical and systematic than just sitting around and waiting for the stroke of genius to hit you on the head. And so here's what we're going to actually talk about. So we'll start with a very brief introduction to category theory, just the bare minimum to get us started. Then once we have that, I'll use the language of category theory to translate ideas from programming into the language of category theory and see how that point of view might be useful for us as programmers. Next, we'll see how we can, building on this, how we can recognize the structure of categories around us and what we can derive from this structure when thinking about new concepts. And the last class of techniques will allow us to generalize ideas in a way that makes them portable between categories. And this will be a very powerful way to explore new ideas. So this is going to be a lot of material, and I'm sure it will be hard to absorb all of it, so don't worry if you kind of get lost in the various details. It takes time to actually grasp them all. But what I want you to have is this kind of feeling of what category theory can give us and what can we actually achieve with category theory, and hopefully by the end of this talk, you'll be motivated to go and explore category theory on your own. So let's dive in. So a brief disclaimer, if there are like mathematicians around or whatever, please don't judge me. I won't be too rigorous about definitions, especially with the absence of most laws. But hope it's going to be okay. So this is the mandatory 30-second introduction to category theory that every talk on category theory must have. So I'll do the same thing as well. So category is defined with a number of things. We have a bunch of objects, A, B, C in this case, and a bunch of errors, which we call morphisms. Those errors must be not any kind of errors, but nicely behaving errors. So specifically, morphisms must compose. So if we have one morphism going from A to B, and another going to from B to C, we must have a composite morphism that does the same thing directly from A to C. So this is quite abstract because objects and morphisms can be pretty much anything, but since this is a programming conference, I'll use the first category I'll introduce is the category formed by the types in our programming language. So this is an instance of a specific category. In this category, the objects are types. So int, string, boolean, and various concrete types in our programming language are going to be the objects in our category, and the morphisms are going to be given by functions. So a function from integer to string is a morphism from the object integer to the object string. And function composition gives us the desired behavior that you would expect morphisms to observe. So from the definition that we have here, what is category theory about? So for the purposes of this talk, it's about composition. So since pretty much the only structure that the category has is morphism composition, category theory is naturally equipped to talk about things that compose. And as programmers, that should be very, very important to us, because working with things that compose is the nicest thing to do, because things that compose just are nice, especially when we're doing functional programming. But more importantly for this talk, category theory is about relationships. So notice how in the definition of a category, we didn't actually talk about what an object is. We just talked about the arrows coming and going into this object. So we don't care that an integer is made of bits or a string is made of chars. All we care about is that these concepts exist and how they relate to the various concepts around them using arrows. So thinking about how things relate to one another is exactly the sort of thing that will help us explore the idea space. So let's begin. So now that we know what a category is, we'll try to take some simple programming ideas and convert them into the language of category theory. That is, we're going to talk about them only in the way they relate to one another, and not by the details of the implementation. So once we manage to do that, maybe we'll find something useful from this translation. So we start with a very simple type called a tuple type. So most programmers are probably familiar with it. So it's a pair of two types. Mathematicians denoted with this times operator, called the product of A and B. So since category theory is about relationships, we need, the question is how it relates to other things. So obviously, if we have a tuple of A and B, so we have an A and B, there's a way to extract an A and extract an B. So these two arrows are called projections that allow us to take an A and B out of a tuple type, product type. So now there are many other things that may be also may have two morphisms going from them to A and B. And how do we actually distinguish any other candidate for being a product type from our actual product type? So what we want to find is kind of the best fit for being a product type, something that's not too big and not too small. It's exactly A and B and nothing else. So we want to kind of filter out all the pretenders that behave similarly to a product type, but not actually the exact product type that we want. So one way to do this, to achieve a definition that filters out other candidates, is to build what's called a universal construction. So the dashed arrow here is called a universal arrow. So it means that there's exactly one such morphism going from C to the product of A and B here. And the resulting diagram is an example of a commuting diagram, meaning that no matter what path we take from two destinations, we must reach the same result. So in this case, it means that if we're going from C and we want to get to A, we can go either through the product and then to A, or we can go directly to A, and the results should be the same. And same goes for B. Now, since the arrow here is universal, it must be a unique such arrow. And this diagram, although very abstract, captures exactly the notion of being a tuple, not too big and not too small. So suppose our product type was too big, there would be more than one morphism that corresponds to a commuting diagram here. And if our tuple was too small, then we won't have any morphisms with this behavior. So this, so we managed to distill the idea of a tuple into something that's a diagram that only relates a tuple to other things. So we're using the categorical language to describe a programming concept. Now, this may seem like a very roundabout way of doing things. So we just used a bunch of arrows to describe something that everybody can just program in a line or two. But there is actually something to gain here, because describing something by its relationships means we can take and reverse the relationship. Quite literally, we can take and reverse all the arrows. And by doing this completely mechanical act of reversing the arrows, we just discovered a new commuting diagram, a new universal construction. And so sort of by magic, we just derived a new concept from an old one. So what is it actually? So it says that we have a way to put an A into it, and we have a way to put a B into it, and because it's a universal construction, it's kind of the best thing that does exactly that. So it's either an A or a B. It's exactly the either type from functional programming. Or in mathematical speak, it's the sum type. And this is quite amazing because with almost zero effort, we derived one idea from another idea. And this is part of a more general principle called duality. So duality gives us ideas for free. Once we formulate some idea in the language of category theory, we can just reverse all the errors completely mechanically and derive a new idea for free from it. And although in this case, either and some types are kind of similar, it's not always the case that dual constructions are all that obviously related. So we get all of this for free just from taking a categorical perspective. So from now on, pretty much everything I'll say will be actually, every idea I'll show is actually, has two ideas behind it. One is the actual idea and the other is the dual. And so this is our first tool to actually explore the idea space. So let's talk more deeply about the universal constructions that I just saw. So if you go down the path of describing things categorically, describing programming ideas categorically, you might stumble upon various universal constructions. So one of them was the product type that we just saw, but there are others. All of them are potentially useful concepts, but if you look closely, there's something very repetitive here. So we also have some kind of a best object over some pattern of other objects, and some other candidates that pretend to be the best as well, but they're not, and a universal error connecting them all into a single diagram. And as a programmer, I find this kind of a bit disturbing, because we like dry code, so we probably want dry constructions as well. Luckily, it seems that mathematicians are very good at taking concepts and really distilling the essence and removing all unnecessary detail. And let's see how we can actually distill the pattern we see here into something more, less repetitive. So what do we have? So we have some category where we want to single out a pattern inside the category. So for this purpose, we'll use another category, which we'll call an indexing category. And we'll use this to use the indexing category from here to try and describe a pattern in the category that we actually want to tackle. So to actually point out a pattern in our category, we'll have to map every object in our indexing category. In this case, we're trying to talk about the product construction. So we have two objects, one for each element of the tuple. And so we assign each object in the indexing category into one object in our target category. Formally, this is a functor, but I won't be actually going into this. And what we call the construction we have here, we call a diagram over the indexing category. So this covers the pattern part of the universal construction. So the next thing we'll do, we'll zoom in on this pattern. So now we want to find our best fit, the one that actually is something that hangs over the pattern and kind of maps into it. So our best, best object should have morphisms pointing into our diagram. So we have two morphisms pointing into the diagram. And this is called a cone over the diagram, because it looks kind of like a cone if you look at this part. And there needs to be some other candidates as well, some that can actually pretend to be other cones as well, and which are not the best cones. So we have other candidates. And because our cone is the best cone, sorry, our cone is the best cone, we have a universal arrow pointing from all other candidates into our cone. And we call our best cone called the limit of the diagram. Now, the limit captures all the parts of a universal construction that we had before. We have our pattern, we have our best object, and we have the candidates, and we have a universal arrow. It might seem that I just replaced one universal construction with another, but actually we immediately gain something new. So in this case, we actually described the product construction, but now, in return, we can actually do something much simpler than we did before. So we just draw a simple pattern. And now we have draw a picture, get a concept. So this very simple picture actually describes the product construction from before. So instead of doing all the stuff with the arrows, we have one simple diagram, and we can just get the concept for free. Actually, we can get two concepts for free because we can have the co-limit as well, which is the dual concept for a limit. And now for every every diagram that every indexing category that we choose, we can actually gain a new concept freely from it. So feel free to explore these diagrams and see what they actually correspond to in the world of type systems. And so every diagram that I'm drawing now here is actually corresponds to one more step in the idea space. So this is a new tool to help us explore various ideas and describe them in a way, and discover them in a way that's much easier than actually doing the whole thing with the product before. So I'm not going to discuss these diagrams. I'm going to discuss one very simple diagram. So it's the empty diagram with no objects in them. And it might seem trivial, but it's actually quite useful in programming. So we start by drawing a cone over the empty diagram. So a cone over the empty diagram is just any object, because every object is a cone over the empty diagram. We now want to find other cones, candidate cones, which are also pretending to be the best cone, but so any other object is a candidate cone as well. And since our cone is the best one, we have a universal arrow connecting the candidate cone to our cone. And we call this object the terminal object of the category, and we designate it with a 1. And there's also a dual object called the initial object, which we designate with 0. So every object in a category can be mapped uniquely into the terminal object, and every object from the category can be reached from the initial object. And in the category of types, the terminal object corresponds to unit, which we know from many programming languages, and the initial object corresponds to void, a type with no inhabitants. And in a sense, the initial terminal objects are kind of endpoints of a category. So when we're exploring a new category, it might be useful to look at the endpoints as kind of representatives of what the category actually gives us, as we'll do next. Okay, so far we've been looking at the category of types. What I want to show next is how we can discover the categorical structure in other places and see how it can be useful to actually discovering new ideas from that categorical structure. So we start with some monoids. So monoids are very common in programming. They're the essence of combining values together. What do I mean by combining? So we have the combine function, which takes two values A and returns a single value. We have the empty value, which disappears during combination. You might notice that this is not the standard definition of a monoid from Haskell, but it's easier to put it into categorical terms this way, as we'll do now. So we want a monoid over some object A. So we have the combine function. So given a product of two A's, we can combine them into a single A. And we also have the empty object, which is a morphism from the unit into A. And this is a bit of cheating because, as I said before, in category theory, we don't care about the contents of an object. So we don't have a way to refer to specific elements in an object. So we're cheating by instead of talking of specific elements, we talk about functions from unit into our type, which correspond to constants. And this is kind of a roundabout way of talking about specific elements in an object. But now we have a categorical diagram that describes the monoid. So we can apply the usual trick of duality and reverse the arrows and see what happens. And feel free to do it on your own and see whether comonoid is something which is useful. But what we want here right now is actually to have some new category to play around with. So I'd like to define a category of monoids. So in this category, every object is going to be a monoid over some type A. But what are the morphisms? What are the morphisms in the category of monoids? So suppose we have two monoids, A and B. A morphism between them will be called a monoid homomorphism. We'll denote it with a squiggly arrow. So homomorphism is not just any function between A and B. It's a function that respects the monoidal structure of the monoids we're talking about. So specifically, it maps the empty value of one monoid into the empty value of the other monoid. So this whole diagram commutes. It should also respect combination. So given that we have two values and we combine them and then apply h to them is the same as first applying h to each element and then combining them using the combination function of b. And so it doesn't matter how, well, again, this diagram commutes, so it doesn't matter what order we use for combination. And so, so any function that makes this whole diagram commutes is called a homomorphism, a monoid homomorphism. And so it happens that homomorphisms compose. And every time you see composition, it's a cue to search for a new category. So behold the monoid category. So objects in our category are monoids over various types, and the morphisms are homomorphisms between the monoids. Can we actually learn anything from this new category? Is it useful for anything beyond just drawing it on a slide? So this new category is obviously related to the old category we started with, because it's pretty much the same category, but with some structure added to it. It's the same thing, but talking about monoids. But since category theory is so naturally equipped for talking about relationships, it's a good idea to try and explore this relationship and actually see whether we can learn something about this relationship. So specifically, we're talking here about forgetting. So if we forget the monoid structure, we get the original category back. So we started from the monoid category, forgot about monoids, got back the original category. So before, when we talked about relationships, we talked about reversing relationships. So in duality, we just reversed the arrows and got back something new. So can we reverse? But forgetting is not something reversible, because when we forget the monoid structure, we can have many monoids mapped into the same object in the underlying category of types. So we obviously can't reverse this relationship mechanically, but what's even more problematic is that are not the objects, because, okay, the objects are pretty much the same, but the homomorphisms that we have in the monoid category are quite unique. Now, most morphisms in the underlying category will not be homomorphisms. So how can we, when trying to kind of unforget from the type category back into the monoid category, how can we tackle those homomorphisms? How can we kind of reconstruct them back when unforgetting from one category to the other? So let's focus on specific functions. So if we pick some random function from A into D, it's not likely to be a homomorphism, but maybe we can decompose it into parts. So we can draw this little triangle, and so we decompose F into two parts, G and H. So G is just a regular function, but H is a homomorphism, such as this whole diagram commutes. So we can think of H as the sort of homomorphic part of F. So F is so if we focus on this part, on the homomorphic part of F, maybe we can kind of unforget ourselves back into the monoid category. But unfortunately, this decomposition is not unique, since we can have other paths as well. So we can go through B here and then go into D using another homomorphism. But this suggestive way in which I've drawn this diagram should kind of point out to something that I'm trying to hint at. So we can think of those functions from A as sort of steps towards the monoid world. And we can move between those steps using homomorphisms. So, and homomorphisms compose, so the steps, moving between the steps is a compositional process. So that's again our cue to search for a category. And indeed, we can define a new category here, a rather weird one. So our objects are going to be those steps into monoids. So F and G here, functions from A, are going to be our objects in the category. And homomorphisms that decompose them, that make the triangles commute, are going to be our arrows, morphisms in the new category. And so this new category should somehow embody the idea of unforgetting monoids from the underlying category. So for some obscure reason, this category is called the comma category. We'll just go with it. So let's explore this new category, and maybe we'll learn something new about the process of unforgetting. So as I mentioned earlier, when tackling a new category, it can be a good idea to look at the initial and the terminal objects. So just to get a sort of a grasp of what the category is about. So let's start with the initial object. So because objects in our category are morphisms from A, the initial object is a function from A into some other object, which I'll call I here for initial. And now, because this is an initial object for any other object in the comma category, so this is any other object in the comma category, there's a unique morphism connecting from our initial object into any other object as well. So this homomorphism is a unique homomorphism that makes this diagram commute. So what we have here is just a new universal construction. So we combined a new category with the old concept of initiality and got ourselves a new idea, a new concept on our hands. But what is this thing? What does this diagram actually describe? So this is part of the challenge of using category theory for anything, is that we must figure out on our own whether some new concept that we discovered is actually useful for anything, or do we care about it. And let's try that. Let's start figuring out what does this diagram actually correspond to. So for concreteness, I'll pick a specific A. So A is going to be a unit here. And we'll use a specific F. So F is going to be a function that takes unit and returns the number 5. And I'll call this morphism, I'll call it inject, short for inject, since it injects into our mystery monoid. So we have inject of unit is some value in our mystery initial monoid. So, so because this diagram commutes, we know that going through inject or going through F is the same thing. So we have an equation. So F of unit, which is equal 5, is the same as applying H to inject of unit. We also know that because H is a homomorphism, it must respect the empty value. So we know that 0, which is the empty value of the integer monoid with addition, should be equal to H applied to the empty value of our mystery monoid. We also know that homomorphisms respect the combination function. So we can, if we know some value in the target monoid, so 5 plus 5, we can write it in terms of the equations we had before, and we can pull H outside because the monoidal operation can be pulled. H respects the monoidal operation, so we can pull H outside. And so we pull H outside and replace it with the operation of the mystery monoid. So I'll call it op because I don't know what it is yet. And we can repeat this process with as many elements as we want. So we can basically combine as many 5s as we want, and we're effectively generating new values in our mystery monoid. Since every value on the left is unique, so are the values on the right unique as well. So basically, we have an algorithm for generating values in the monoid we're trying to actually discover here. So the structure of actually what we're doing here is obscured by bad naming, but if I'll do a quick rename, we see that what we have here is structure of arbitrary length lists of unit. So the monoid action becomes the list concatenation, and the inj function, the inject function, just wraps unit into a singleton list. In general, the initial object over A is just a list of A's. Inject builds a singleton list. The unique homomorphism is supplied by the fold map function from the Haskell standard library. And what's very nice about this new construction is that it has no junk, in the sense that the monoid that we built here, the list, has no extra elements beyond what's required to be a monoid, and has no noise, in the sense that there are no extra equations beyond what the monoid structure actually requires us to have. So what we have here is the minimal way to build a monoid over any A that we have ourselves. So by exploring this category, the comma category, which was kind of the embodiment of unforgetting, we managed to deduce the minimal way to unforget something from the underlying category. So circling back to the quote from the beginning of this part, when you see composition, it's your cue to try and find some category that's lurking around. And if you find that category and you try to explore it, like we did with the comma category, maybe you'll discover something new about the structures that are involved in building up those categories. So hopefully the exploration of the monoid category and the comma category are an illustration of this point. So far we've been looking at concepts from within a specific category. We'll now see how we can generalize ideas that we have in one category, generalize them, and make them move them between categories. And this will be a huge boost to our ability to explore the idea space. So let's look at the monoid definition again. So if we look at this definition, it's not quite portable, in the sense that it's tied to a very specific category. So the fact that we're using unit here is kind of hard-codes the category of types into our definition. So just like programmers who like portable code, mathematicians like portable definitions, because it's nice to have one definition, just use it all over the place. So let's try and generalize the monoid into something that can be reused across different categories. And the unit here is actually not the only problematic thing. The other thing here is the product of two A's. So the product construction, as we've shown before, is a very specific thing. It's something that has two A's in it, and it's a very limiting construction that we won't be able to actually move generally into any other category. And so what I would like to do is kind of generalize but if we actually look at how we use the product in the monoid definition, we don't actually care about having two A's. What we care about is we have some notion of two-ness, that we have a function of two objects, but we don't really care about what the function does. It just has two objects. It's applied to two objects, but it might have anything in it, anything else inside, not specifically two instances of A. So we'll just generalize the whole thing and just replace the symbol. Mathematicians do this a lot. They just replace symbols, and it just all works out. So this is called the tensor product. So this little circled X. It's basically any well-defined function of two A's. And so the product construction is one specific instance of the tensor, but there are many other instances of tensors as well. Now we can tackle our unit here. So the unit, I said before, was our way of cheating into getting ourselves values of type A, but actually it has another role here. So it also serves as the unit, or as the identity of the product So it means that A product with unit is equivalent to A itself, because the unit doesn't really add anything new. So we'd like to have something equivalent with our tensor product. So I'll call this I, short for identity. So the identity of the tensor is going to be equivalent, A tensored with its identity is equivalent to A. And so we can replace the unit with this I that corresponds to the tensor that we're using. So now this definition is very, very general. It can be applied in many different contexts, and it's much more reusable in the context of category theory. Now, to actually show how reusable it is, I would like to introduce a new category. So something that's radically new and not similar to what we had before. So the category of endofunctors. So objects in our category are going to be what category theory calls endofunctors, and confusingly, in programming, there's just type constructors with a functor instance for them. So the type constructors f and g, which form a functor, are objects in the category. Our morphisms are going to be what is called natural transformations, and I won't be going into them, but in programming, they just correspond to parametric functions that take any f of a to a g of a. So parametric functions between type constructors are natural transformations, and these compose, so we have a category here. And so for examples of natural transformations are functions that say take maybe of A and produce an A generically. They don't look at specific A, they just do it generically between the two type constructors. And for us to actually have a monoid, we need to have a tensor as well. So we'll pick a specific tensor product. So a tensor product of type constructors F and G is going to be F applied to G of A. We also need the identity. So the identity is going to be the identity type constructor, which when composed with any idle type constructor just yields the same type constructor as we started with. And now with all of this data, we're ready to build the monoid in the category of endofunctors. So we start with the generalized monoid. Since the elements are functors, we're going to replace all the letters. Now the identity object is going to be the identity type constructor. Now, since talking about functors generically is kind of cumbersome, we're going to quantify the whole diagram. So I'm saying that this diagram applies for any, so this diagram can reference A in it, but it's going to be applied to any possible A that you'll supply it with. And so we can actually use A in the diagram. So identity of A is just A. We can apply F here to F of A, to A and get an F of A. And we can apply our tensor product, which is functor composition, to produce F of A. So what do we have here? So let's try to repeat this whole process again, but using actual code. So this is the monoid definition using the generalized monoid definition using code. So first we apply, we move it to the endofunctor category. So every instance of A becomes an F with a functor constraint. Next, we replace functions with natural transformations. So with parametric functions over any A. We can replace the tensor product here. Can point there. Here with functor composition, so it becomes F of A. And this is starting to look familiar. Quick rename. So what we just rediscovered, rather mechanically, is the definition of the monad. We can even define the more conventional bind operator using the functions that we have here from our definition. And this is what gave birth to the now famous or infamous quote that the monad is just a monoid in the category of endofunctors. And so generalizing and moving between categories is a very, very powerful technique. Look how far apart are the concepts we just connected. Can you imagine connecting monoids and monads without the kind of wide perspective that category theory gives you? So more generally, generalization is knowledge reuse on overdrive. So everything we know about monoids, the regular monoids, we can kind of reapply in the new context. So if we know about free monoids, we now know about free monads. If we know about duality, so we know that comonoids are now, we now rediscovered comonads. And so we can also maybe, I didn't talk about them much here, but we have laws and proofs about various abstractions, and so we can reuse the same laws and proofs to the new abstraction that we just discovered. And maybe in a sufficiently advanced language, we can actually do code reuse, writing code once that applies both for monads and monoids in the same library. And now we have only one set of tests, one set of library functions, and everything is much more reusable. So imagine achieving such reuse without the powerful tools that category theory can actually provide you with. So now we're ready for our last part. So I'll try to get a bit closer to actual code rather than just diagrams. So it's a case study. It's not really a case study because there's no case, so I'm sorry. So suppose I'm writing a function that takes a list and returns some monoids. So I tediously spell out the recursion over the list, go over each element and combine it using the monoid action, do something and get the monoid back. But then I recall that a list of A's is the free monoid or the initial object over the relevant comma category. So from there we know that there's the fold map function, which we have for free using the definition, the initiality of the free monoid. So now we can, instead of tediously spelling out each and every step of the recursion, we just spell out how we apply our function to a single element of the list, and fold map just takes the rest and just does the whole recursive thing on its own and produces a single result. But now we just learned how to generalize. So we can generalize this signature and move it from the category of types into the category of endofunctors. So now we have a new type signature, fold free, which is actually a useful library function, which actually exists in various libraries that work with the free monads. And we also just learned about duality as well. So we can dualize this signature and get something. So we just discovered co-free comonads. Completely for free. We didn't actually have overloading of the word free. I'm sorry. So we just rediscovered co-free comonads just by mechanically moving around between categories, dualizing, and stuff. And again, this function, which is just mechanically derived from another function, is a useful function when when working with co-free monads. So look at this three-type signature. Look how different they are, and what a huge kind of journey in the idea space they talk about. So these are the sort of exploration tools that you get from category theory just by kind of adopting the categorical way of thinking about relationships. You can move around various ideas and connect them in a way which is very powerful. So speaking of those tools, so we can take a step back and kind of admire what we did through this talk. So we started with the very simple concepts of products and monoids that we know from everyday programming, at least functional programming already. And we used duality to derive new ideas for free. We used initiality to derive the free constructions. We also used generalization to move between categories and derive new ideas. And we can keep on applying these tools, and so we can discover more, keep on discovering new ideas, going further around the idea space. And this is just scratching the surface. So category theory gives us many other tools at our disposal to explore the idea space. So we have the Uneda lemma, junctions, con extensions that I mentioned at the beginning of this talk. And all of these are reusable because they're so rigorously defined and talk about composition. It can all be reused in various contexts and mixed and matched to describe various new ideas that are actually useful in functional programming. So we can keep on going around and around, reaching ever-expanding areas of the idea space. And we're just scratching the surface, really. There's so much more that you can discover using category theory. So imagine having all of these tools at your disposal. What sort of things will you be able to discover using category theory as your tool for thought. And since this is all I have for you today, I'll leave you with this rather cryptic quote to ponder about. So one day I hope to actually make sense of this thing. Thank you.
We have time for one question.
Shell-shocked.
Okay, right.
So were you able to actually use it to devise a better data structure for your product?
I'm just starting out, but people like Edward Kmet actually have libraries there's a Khan extension library that optimizes the usage. We had in the previous talk the polysemy thing, so it's a continuation-based optimization over some free monad, so that's some Khan extension of something to something. So I'm not an expert enough, but there are libraries that actually use those techniques to actually do real library code. So you just need to know them. It's a huge learning curve, but it's worth it, I think, probably, when I learn them myself.
But Edward Kmet is not a human being.
Yes, that is a limitation of us simple humans, yes.
Okay, thank you, Daniel.